All right, take it away, Caleb.
Okay, so you should be able to hear me. You should be able to see my screen, which is currently a GitHub repository. I use this particular repository for a lesson last year. So I'm just going to reuse it for the purposes of this diagram. So this is where all of the code is going to come from. I have it up on or in Writer, so we will take a look at that as well. I would like today's session to be fluid, so as you have questions, just go ahead and blow them out and ask them. Worst case is I'll say, hey, I'm going to get to that. It's a great question, and then we'll come back to it later. So presentation format is I have a set of different tabs or groups of tabs that we are going to cover. So there's no slides. We're going to look at real content, and we're going to have a lot of fun going through a semi-real application. And as if we didn't know the application, and figuring out how we can figure out what its performance woes are, how we can improve it. And we will walk through the process in that order. So with that, let's go ahead and get started. So I'm going to, first, let's go ahead. I have the code here. There's a few different controllers, but I'm just going to go ahead and we'll fire it up. Okay, so as background, I have this application set up with a JMeter file that I can use for load testing. So I have JMeter running as well. I'm going to go ahead and I'll grab that and I'll pull it over. So JMeter is a load testing tool. You're not supposed to use the GUI for running an actual load test, but for the purposes of today, it will be plenty accurate. So I'm just going to go ahead and run directly in the GUI. Main purpose of this is just to kind of get an idea what the application's current performance is. So I'm going to go ahead and hit start, and we can see the throughput over here, as well as the sent and received bytes. So at this point, the application is up and running, and if we look at these, like pretty soon we'll kind of hover around to one message per second for most of the calls. So not super fast, right? We definitely have some room for improvement. So that's kind of the baseline of where we're at. So I'm going to go ahead and clear this setting so that we can jump into more of the content that we have today. So we have log outputs that we could use if we wanted to. We probably won't even need it. So I'm just going to let that sit there and run. It's just going to be idle. Okay, so with that, you've seen the code. It runs. Aside from a couple of minor changes, the code that is up here, I updated earlier today, is accurate. So with that, let's start talking about some of the tools that we have available. Now, a little bit of background. I came from Linux development. Specifically, I did 12 years of Linux before jumping into .NET. So when I came, I started looking for tools that were equivalent to some of the Linux ones that I knew about. And in the process of doing that, I found a lot of tools existed, were either poorly documented or nobody knew about. But I want to just say straight up, Windows has very, very good tools that might be very hard to use, but are available for performance troubleshooting. So with that, one of the first things we're going to talk about is event tracing for Windows, which is what ETW stands for. Now, this framework is built into the kernel, and we're actually just going to talk about the diagram here. So the Windows kernel has support for this mechanism, and that allows it to be very high speed. It also means it can be used for debugging kernel level issues. So there are events that are emitted those events are then stored into this buffer pool. Actually, I'll just draw on the screen here. Right, so they will be stored here in this buffer pool. And as long as they are consumed in a timely manner, then they can be recorded just about anywhere. So there is this high performance subsystem called Event Tracing for Windows that has a number of different components. So one of those, which we see right here, is this controller. And the controller is what says, hey, I need you to start a tracing session or stop a tracing session. And then there's a lot of different parameters that you can specify. And those parameters will do things like say, hey, I'm only interested in network events, or I'm only interested in exceptions, or I'm only interested in things in relation to .NET, for example. So we can customize that, but there are a number of different applications, and many of those have different profiles or different defaults that you can use depending on the type of troubleshooting that you're doing. So with that, we have a set of different ETW providers. And then there can be any number of consumers. And today we're going to look at both of these. We're going to look at consumers and providers. So with that, I want to jump in, introduce you to some of the providers. We're not going to spend a lot of time on it. I'm going to go ahead, clear the screen, and let's make this font large enough that you should be able to see it well. Okay. Okay. Okay, so I have a console on the screen now. One of the commands that is available to us, and I cannot guarantee for this particular tool whether it is included by default in Windows or if it came with something else that I installed. I will call out some of the things that I have installed later as we're going, but there is a tool called Logman. And if we just hit enter, basically what we can see is that there's these data collector sets, there's various types of them, and then there's status, but I don't have any running. And what it's telling me is I don't currently have any ETW traces or sessions running. So there was never a controller that started a trace. And Logman is actually one type of a controller. So if I run logman help, let's do a try dash question here, then what we can see is that there's lots of different commands. So I can start a trace that exists and has been named. I can create a trace that is going to grab performance counters. And then in this case, there's a single performance counter that's being grabbed. We can set up alerts for, in this case, a processor CPU of over 50%. So there's a lot of different things that we can do with Logman. I'm not going to spend a lot of time here, but the thing that I thought was of most value was to call out the different providers. So if I do logman query providers, and I'm going to go ahead and I'm going to do a select object dash first. I'm going to do just select the first 30 of them. And then while that's running, I'm going to go ahead and grab another command. Now, there are a lot of providers. Select object isn't going to output anything until all the output is done. So now we have output. So we could look through the list, and each one of these is going to provide different types of messages. As I said, I might not care about some of these providers for the type of debugging or troubleshooting performance investigations I'm doing. There are others that I might care a lot about. And it could depend, right? So for example, ATA port. Well, I don't do anything with ATA ports, so that one isn't particularly special to me. Now, each provider does have a GUID, as you can see. Now, I'm going to go ahead and select one that will probably be of interest to the group. And this one is related to .NET. So you can see that there is a provider just for the .NET runtime, which is this Microsoft Windows .NET runtime provider. And sometimes we'll see the GUID depending on the tool that we're using. Other times we'll see the name. Now, when we choose to do a trace or a capture, I will typically enable providers of interest if the defaults that I am interested in are not of value. And sometimes that means we just want to search through it, right? So we could basically do a search for anything that had the word .NET in it. I could do Microsoft Windows, and you could do a search to see which ones exist. Once you know which ones exist, we can inspect the details that are supported by this. We can look at the list of events, and we'll do that a little bit later in the process. Okay, so now that we've seen the providers, some of which will be available to us and useful, and others which will be less useful, we've seen the architecture. One of the things that let's see, I already did mention the fact that we can do kernel mode, which is potentially useful, but this is Windows specific, right? Hence for Windows. How does this work for, say, .NET Core? This is not necessarily a Windows specific session. One of the things that you'll see as I go through the presentation is that we can collect good data on both, but as of right now, most of the tools that allow us to really consume this information are still Windows centric. So it's kind of a downside, but Windows systems are still sufficiently available that it's not particularly problematic for most people. Now, on the Linux side, there is something called LTTNG. Which is used for, or at least was used for, the instrumentation. I'm just going to add a caveat right now. I have not kept up with all of the .NET Core development. So when they started on the event subsystem for .NET Core, if they were running on like Linux or Mac or something like that, they would use LTTNG. They may have moved away from it, but regardless, we get the same information. So in other words, there is equivalent capabilities, roughly speaking, for doing the same investigation on Linux. Today, I am not working in Linux. I do a fair amount of development in Linux still, even on .NET. It's just not what I chose to use at the moment. So, and we've already looked at Logman. So now we know that we have both. We have support for the Windows side, we have support for the Linux, Mac, and other side. So now let's kind of jump in and talk about the tools that we have. So one of the first things that we're going to take a look at is we're going to look at dotnet-trace. So dotnet-trace is a .NET tool that can be installed that gives us the ability to grab captures that come from the underlying subsystem associated with the operating system on which the application is running. So in Windows, when I use dotnet-trace, it is going to use ETW events. And if I'm on Linux, it will use LTTNG or the underlying supported platform and its corresponding tools. I have already installed this, so I do not going to install the .NET tool. In the event that you had this installed earlier and your command line options differ, know that you can do an update of the tool, and then you should have version 6 of it available, at which point your command line parameters should match what I have. So with that, let's go ahead and jump into what that looks like. So I'm going to go ahead. We're going to pull up a command line again. So I'm going to go ahead and run dotnet-trace and help, and let's see what our options are. So we can perform a collection where we get information from one of the underlying subsystems that provide details about the events. We can get a process list. We can list the different profiles that are used for capturing. So let's go ahead, let's do that dotnet-trace. Let's list profiles. And one of the things that we're going to see is we have a CPU sampling, but then we have a couple for garbage collection. And then newer in .NET 6, we have one for entity and ADO entity framework and ADO.NET capability via this database option. So these will grab various events specific to those types of problems. If you are interested in all of these, you can write custom command lines that will aggregate it, that will basically union the set of providers that it's going to capture events from, and then you could have all of that information. Okay, so with that, let's go ahead. I'm going to run dotnet-trace PS, which is to get my process list. And then you can see I have my App Insights test application right here, and it's running, and I have the process ID. So with that, let's go ahead. We're just going to jump in and let's do a trace. I'm not going to specify all of the options available in collect, but I will specify a few of them as examples. Okay. Oops. Not copy. Let me grab that. Okay, so I have I'm specifying my buffer size. This is in megabytes. So right now I'm saying, hey, I have a 384 megabyte buffer, which is quite big for doing a collection of a single process. If you have a process serving millions of users, you might go through it pretty quickly. You can change the buffer size. The default is 256. I'm specifying my output trace file name and then the name of the application. This is just more convenient than using the process ID because the name is usually fairly consistent. But before I do that, I want to make a temp directory for this demo 1. So let's go ahead. We'll CD to that directory. And then I didn't paste that. So, okay. So now I should be able to go ahead and start a trace. And sure enough, it's running. We can see the trace growing, and there's my application. So as we can see here that there's a couple of different things that are providers that have been included. One is this .NET Core sample profiler. And what this is going to do is it's going to grab stack traces so that I have samples of the stack traces for the application. If I were doing one of the other options, like garbage collection, I don't need this, this provider. But then I have the .NET runtime as well. Keywords and level, I'm not going to really get into. They are used, well, I should say level is valuable if you're not seeing events that you care about and that you know exist, or if you really need to get down into the weeds. There are additional events that we can enable. And then keywords can be used to selectively filter out different events of interest within that provider. So definitely useful in there. Okay, but at this point, we haven't sent any traffic. So I'm going to go ahead. I'm going to pull up JMeter again, and let's go ahead and run. Okay, so now we're starting to get traffic. Performance is slow. This does have a ramp up time. I think I have it set to like 15 users with a ramp up time of 60 seconds. So we're going to go ahead. We're going to let it run just a little bit. And let's go ahead and go back. So now you can see we're growing a little faster. Before we were looking at kilobytes. Now we're looking at megabytes. It's been running for a total of 1 minute and 40 seconds. Now, a couple of notes. When I introduced the architecture for ETW, what I said was that if the events are consumed within an appropriate amount of time, those events are available for any consumers who are interested in them. One of the things that I didn't say is that the underlying data structure is a circular list, which means, or circular buffer, which means this 384 megs that I specify, if I were to hit that, it's going to keep the last 384 megs. So at this point, I have a 2.5 minute capture, which is more than enough. Some of it was sitting idle, but I'm going to go ahead and hit Control C because I have data. So now the trace is completed. As we can see, I'm going to go ahead and stop the load test because it doesn't need to run. And let's look at my directory. So at this point, I have generated this my trace file, said it was about 31 megs. That looks correct, right? So I have 31 megs. There are other formats that are supported. So if we go back to dotnet-trace, there is a convert command. And I'll go ahead and run that so we can see what our options are. We have the ability to use a Chromium format, which is one that is supported by the Chrome debugger. So if you're familiar with JavaScript debugging and happen to use Chrome for that, then you can actually use that particular profiler. I shouldn't say debugger, but that profiler and its supporting capabilities to look through and examine the content that we have here. The net-trace format is the default. And then we also have the speed scope format. And for purposes of this, I'm going to go ahead and I'm going to convert the file that I have to both formats, just so that we have them for later consumption. Although I probably won't actually go into the Chromium one. Now, you'll notice that it's creating a JSON file. It is vaguely human readable in as much as JSON is, but it is fairly hard to read. It's not very useful unless you actually dig into the file format. So in general, we're not going to care the fact that these are JSON files that in theory we could look at. Yeah, like I said, just not particularly useful. Okay, so any questions before we jump in and we start looking at the results of this file? No. Okay. So now that we have these files, what do we do with it? We want to understand the performance of our application. Right now, there is a single option that is built into the dotnet-trace tool that is cross-platform. And that is this report top-n subcommand. So report basically says generate a report. Top-n is the subcommand, and then I'm telling it I want give me the most common or the worst 15 stack traces, or I should say, I guess it would be give me the frame that represents the top of the stack for the worst 15 occurrences. So let's go ahead. I will run that, and it won't take too long. It's actually going to output it to the console. And there we go. Okay. Now, because this was my App Insights test application, I did disable application insights in that it's not going to report its content to application insights, but it's still installed and running. So let's go ahead and look at this. So transmission storage, this makes, I don't want to say it doesn't make any sense to me. This happens to come from application insights. Manual reset event slim. Well, this is really in relation to locking, but I don't know where that locking came from. So this is perhaps something that we should investigate. Default aggregation period. Again, not my code. Not sure where that one came from. Thread.sleep could be good, could be bad, right? If we have code that's purposefully blocking threads in .NET Core, that means our thread pools threads are being stuck doing stuck waiting. That would be bad. If on the other hand, it's in a dedicated thread running on a loop or something like that, then it might not be bad. So maybe worth investigating. This one's interesting. Console pal, Windows console stream. So we're writing to the console. I didn't really intend that, but if I spend a little bit of time thinking, what I realize is, oh, wait a minute, we have this output going to the console, which in this case is being consumed by my IDE here. But apparently that's a fairly costly operation. And we can get more information than we see here, but this is what the built-in report gives us. Okay, so we have a wait handle. We're waiting for something to complete. Create directory handle. That happens to be related to App Insights as well, because I already looked at that one. Again, we have more console writing. Oh, interesting. Now, this one is in relation to our code. So let's see what we can learn. So apparently the perf controller has a random delay between milliseconds method here, which takes a couple of integers, and it spent 4% of its time. Actually, let's look at the exclusive time. 4% of its time in this method directly. So because this is something that we control, let's go ahead and take a look and see if we can figure out what that is. Okay, so we're going to go to, that was the perf controller. Oops, wrong key. Perf controller. And it was the random delay method. Random delay between milliseconds. Yep, we have a min and a max. Oh, and sure enough, we see two different things. We see the thread.sleep. Instead of properly doing an async await. The difference being that this thread, the thread processing the request that I have made, is now stuck. It cannot help anybody else while it's waiting for this operation to occur. And that's bad because there's a limited number of thread pool threads. We want these thread pool threads, the worker threads, to be able to take on any work that's available to do, so that at the time the work is completed for a particular thing, one of those worker threads can be notified that the work is ready and then go off and do that work as soon as one of those worker threads is available. So let's go ahead and fix this. So let's go ahead, we'll make this async. This should really be an await task.delay on delay. And then this return should be the delay. Okay, so now I'll go ahead and save that change. So just looking through this report here, we figured out one thing. It'll be interesting to see if this disappears or if there's other cases, but we'll come back to that. And that's it. I don't see anything else useful. Again, oh, actually the console output. We should take care of that as well. So this is, again, more console output. I had never heard of Console Pal prior to actually preparing for this. And it turns out it is a class in the CoreFX. So it's part of .NET. It's an internal class, so we don't see it directly. And then this one is kind of interesting. So missing symbol. So by default, the system tries to grab symbols based on how you have your system configured. So for example, I have my symbol server environment variable defined. So I have a cache and I tell it which symbol servers to go to, but it wasn't able to resolve one of them. So that's kind of unfortunate. It is something, there are other ways that we could work through and we could figure out what that is. And we might talk about that a little later.
Hey, Kaleb.
Okay, yep.
Can you explain again? I think you did, but I missed it. The difference between the inclusive and exclusive?
Okay, so inclusive time is the time, that is a good question. We're gonna, and I was going to explain this in a second thing, which also has the same thing. But inclusive time is the time in this method and all of the methods it calls. The exclusive time is the time in that method directly. So if you have exclusive time, that means this method right here is a bottleneck or has this as its impact. So that is a huge impact. Now, I'm not going to go ahead and fully remove application insights yet. So this one we're going to leave, but that's the difference between the inclusive and the exclusive.
Thank you.
So, yep, great question. Thank you. Okay, so from there, like I said, we identified a couple of performance issues. Let's go ahead and let's fix that logging one really quickly. And then we should be able to run. So I'm going to go, I don't remember if it's in program here or startup. Okay, so right here, if we're in debug mode, write to console. So in this case, the change is actually pretty simple in that I could just change my configuration. I'll go ahead and stop running it. I don't need to run it now. I could just go ahead and change the configuration, but I'm just going to go ahead and delete it because it's a demo and it's easy. So with those changes, I should be able to rebuild here. And now we should get better performance the next time we do a trace. Okay. So on to next steps. As I mentioned, the tools available for consuming these trace files are still mostly Windows-centric, which is unfortunate, but is reality. Now, because most of these tools are open source, like dotnet-trace is open source, some of the other tools I'm going to show you are also open source, we have the ability to go through and add new commands. So I would love, for example, in that dotnet-trace report, I would actually love to add one that inspected for thread starvation issues. And then identify the methods where that occurs. And those are things that we have the ability to do, and we could programmatically determine with a fair amount of effort, or quite a bit of effort. So I expect that we will see more and more commands added. Like I said, dotnet-trace, this particular report, which is the only report here, is new as of .NET 6. As of .NET 5, this didn't exist. You had to go to other tools. Same thing with the command that we were looking at earlier, where we had the ability to capture database. This was also new. So improvements are coming. Expect more. Okay, so now additional tools. So I'm going to show you without much explanation about the tool what one of those tools is. One of those tools is PerfView, and I'm going to use one of its commands without the user interface to give me the manifest file that shows me what the events are. Now, most of these are documented on the web, so I don't necessarily need to inspect this particular manifest, but I'm going to go ahead and run that. And if I do dir here, then what we'll see is now I have a manifest file. So I'm going to go ahead, I'm going to pull that up, and then we'll take a look at it. Okay, so earlier I said there is a GUID associated with every provider. That GUID is defined right here. They must be unique. The GUID is what is used to do a correlation between the provider and the events received, and to do some mapping. We can see the keywords. I said I wasn't going to explain much about keywords. We can see their values. So by using these masks that we see here, we can filter the events to those of interest. We also have some understanding of the format of the message that they will generate. So these are defined down below. So if I do a search for this, for example, we can see that this particular ID, the one I just searched for, has this as its value. So in this case, this is the value, but it doesn't have to be. This could be a full sentence. It could be something else, right? This is just how the conventions that they chose to do this. Okay, so I'm going to go back up to the top. Okay, so additional information about these. So typically, what happens is the manifest file is registered with the kernel, because the kernel has to understand the events that are received, and it has to understand the data types and the parameters associated with it. So if we go down, we get to this task. So there's a task for GC, for garbage collection. And then there are different opcodes. Think about it as of operations that exist under this garbage collection category. So we have suspend, start, we have lots of them. Root condition, weak table element, and I don't need to talk about all of them, and I don't know what all of them are. But there are some that are very useful. So for example, this IO thread creation. An IO thread is something that sits waiting for like an input-output operation to complete. So for example, if I'm receiving data on a network card, I don't need a thread sitting there waiting for that data saying, hey, are you here yet? Are you here yet? Instead, it starts up an IO completion thread that will, and there's actually a pool of them, but I don't need to go into too many details, right? So there's this pool, it'll start new ones on occasion, and these threads will wait for operations, and something like a DMA or IRQ request comes in, it triggers that thread to say, hey, by the way, I have data for you now. And then it runs and it can do good things. So we can look through these different tasks, their corresponding opcodes for things of value. There are IDs associated with these that show up. Some of these we can see in the your Microsoft Event Viewer, right? So just know that that's another way that we could view some of these. Now, most of these are not going to go to the Microsoft Event Viewer because it just doesn't care about a lot of these events. Okay, so I'm not going to say much more. Just note that here's a manifest. I use the PerfView tool to get it. So what is PerfView? So now with that, I'm going to jump over to PerfView here. Okay, PerfView is another open source tool. It has been around for quite a while. The user interface is not pretty. It's not particularly easy to use. The documentation is good, and the tool can do some amazing things. You can get it by coming here and then going to the releases. I typically get mine through Chocolatey, so I don't have to always come back here. So that's how I get mine, and I keep mine updated, but you can grab it directly. Okay, so with that, I'm going to go ahead. I'm going to fire up PerfView, and I'm just using the command line because I can, even though I'm pulling it up in the GUI. Okay. So here we are. We're in ctemp demo 1, and you can see my traces right there. So that's convenient, but I want to give you a brief summary of the tool and its capabilities before we really dig into that one. Okay, so collect. I have the ability to actually do the collection directly from here. So most of the time, I don't use dotnet-trace to do the captures. There are some minor differences between traces generated by PerfView and traces generated by dotnet-trace. One of them is the file format. PerfView can read a net-trace file, so it can process it just fine. .NET, I should say PerfView, will generate an ETL file, which is the file format used by the event tracing for Windows subsystem. And there's a bunch of other tools that can read that same file format. I'm going to go ahead and hit collect. It's going to prompt me for my administrator information. So let me do that really quickly. Okay, so let me pull that over now. Okay, so now it's an administrator prompt. And I wanted to do that so I could show you a number of things. I now have the ability to focus on a specific process, which is what dotnet-trace did, or I can do machine-wide. Machine-wide can be very valuable at times because now I have insight into what else the system is doing. Like if my application runs perfectly most of the time and nothing changes in its in the code, and it's always doing the exact same thing, and then all of a sudden something else seems to slow it down, then I would want a system-wide one. Okay, so with that, I want to talk about some of these settings. So I can grab all sorts of information by clicking these checkboxes. Let me see if I can zoom in here. And remember how I scroll over. There we go. Okay, so if I were to choose file IO, then what it's going to do is it is going to record all of the file IO operations that take place. There are a lot of different presets, and each one of these is going to enable certain providers so that I have information about those events, and they can be extremely useful. So the ones that I typically use for .NET, I use, let's see, note that you can hover over. Some of them, and it will typically warn you, are expensive. So for example, .NET calls, it basically is going to trace every single call to a .NET method, right? That is very costly, so we don't want to do that. I always want thread time. In other words, I want to see when threads are doing what they are doing. The other thing that I will typically always enable is tasks. If you're doing a command line application that doesn't use threading or tasks, you might not need those. But understanding how data flows between tasks and how that workload is distributed is very useful. So I'll typically enable those things. And then after that, it will vary. Typically, we don't need this anymore. .NET symbol collection, you will want this if you're going to do the analysis on a different machine. If you're doing it on the same machine, it doesn't really matter. So for now, I can disable this. The circular megabytes, this is the buffer that I told you about earlier that I had set to 384. And then you can choose to zip it. If you zip it, all of the files that it uses that will include information about the symbols and things so that it's useful on a separate machine get zipped up together. If you zip it up, then all of that is effectively merged into the same content. So use zip and merge and .NET symbol collection if you're going to use it on other machines. However, for most things, like I said, if you're just doing it on the same machine, it won't matter what values you have for those ones. Okay, so that is probably good for now. So let me go ahead. I'm going to go ahead and run another trace really quickly. We're going to do it with this particular tool. So I need to start up the application really quickly. So go ahead and run that. And then here in just a second, we should see it start up. But hey, it's a demo, right? What better time to fail? It's going to have to fail. Oh, actually, we're not going to see it start up. I'm sure it's running, but I forgot we disabled the console output, so I'm waiting pointlessly. Okay, but that means I should be able to go back to our load test here. Let me go ahead and clear it. Let's go ahead and run, confirm that we're getting traffic. Okay, so it's responding. And we're already faster than we were before, because before we were sitting around like one per second. We're going to scale up over 60 seconds. So we're going to go ahead and let that run. Now let's go back to our session and let's go ahead and start collection. So I'm going to go ahead and hit start collection. And it's going to give us the size. Because I'm doing machine wide, it's going to grab a lot of information. As you can see, we're already at 250 megs, 270, 300. Okay, I don't need a huge file. So I'm going to go ahead and hit stop. Now, it is going to take a little bit to start processing all of that. So basically, it collected those events that were going into in-memory buffer. Now it's going to have to do something with those events. So you can see that it's processing. I'm going to go ahead and drag that off. Excuse me. And once it's done, we'll go ahead and take a look. It's actually done already. Perfect. Okay, so this is the PerfView user interface. So these are the original traces. I didn't change the file name. It tells me it's not merged. So because I checked thread time, I can get information about the different threads. I have more information than we do with the net trace file. We didn't look at that, but I'm not going to have as many of these sets of information as I will by default with dotnet-trace, or I should say with PerfView, as I had it configured. Okay, so first thing, I'm going to pull up this processes one. This process list is going to show me all of the different things that were running on my machine. And I'm going to make sure I can share it. Okay. So for example, I could see I have some curl commands running. Not going to explain that, but that is accurate. You can see that I have Windows Event utils running. And then I have some bash and other stuff running in WSL. So I could get a full list of all the processes that ran in there. Now what I'm going to do is I need to actually drill in on a specific process, which is the process that we care about. So I'm going to go ahead, I'm going to find our application. And I am looking for app insights test. Okay. Okay, so now I've filtered it to the particular process, and then the rest of it we can look at in detail now. So here's our process. You can see the chain. So it was started by writer and so on and so forth, all the way up to app insights test. And I can get information about the PIDs and whatnot. But what's really going to be of value to me are the stack traces. So I'm going to go ahead into thread time, and we'll filter to that process. That part should be pretty straightforward. It opens everything up in a new window. Because this is a bigger file, it's going to take a little bit. And let's see if I can get this on screen here. There we go, right here, loading symbols. So this is a zoom in of the bottom left. Now that I'm starting to look at the stack traces, it's going to retry and resolve all of the stack traces. I have a lot of the symbols cached on my machine, so it doesn't take too long, but it is on occasion going to find new ones that I hadn't used before. Or if I update .NET version, right, then at that point, the symbols are slightly different. So it should have opened another window because it is done. So I'm just going to go find that. And now I get to choose the process. And here's the app insights test. So I'm just going to go ahead. I'm going to double click. And now we're drilled into kind of the same information that we had collected in dotnet-trace, but that we couldn't inspect. So we have two different types. We have non-activities, which is background work that's taking place, or work that's requested but isn't actually in that foreground thread, the user thread that's processing. And then we have activities, which are like the user-facing threads. So if I click on one of these, you can see the paths that are being requested. So I can see what the requests are. So we have a bunch of requests for perf. We have a bunch for cart and different cart IDs. That makes sense. You can see, oh, it looks like it's still sending stuff to App Insights. So maybe I didn't disable it like I thought I did, or maybe that got reverted. Anyway, so we have a bunch of different information. So all of this can be extremely useful to know and to understand. So let's take a look at some of these non-activities. So now you can see here's those IO thread pool threads that we talked about. We have our .NET threads. Now, what can we do with this information? Well, let's start. I'm going to go back to this name view, and I'm going to go ahead and I'm going to remove all of the filtering to start. So I'm going to go no grouping, and then no fold. And what this means is that I don't care whether it's in a system library, if the code is in a library that I wrote or somewhere else, I want to see everything just at the rawest level. And that can be very useful at times. What fold % does is it says, hey, if something has less impact than this threshold that I have here, for example, I could say 1%. In other words, if a method calls 2 other methods, and each of those methods has an impact of less than 1%, just group them together into that parent method. Now that parent method, because we group together, let's say if they're both 1 or whatever, 0.99, then that parent method then ends up with a consumed CPU time of 1.98, which would exceed that one threshold and therefore would show up. So looking at the stack, you can see, okay, I spent a fair amount of time waiting. And if I look at, this is your exclusive time. This is the exclusive %. So this goes back to the same question that Kelly asked earlier, where it's like what's inclusive versus exclusive. It's the exact same thing, only now we have counts as well. So we have our inclusive here, we have our exclusive, and then we have counts for both. The when, this is a timeline, and the character that shows up here represents how much CPU was used. So for example, a 0 represents like a 0 to 9%. A 1 represents 10 to 19%. An A, that one might be like 46%. Anyway, the help is really good. So I could click on this, so I can just hover and it shows me. So A was 100% to 110%. Okay, so this was the filter that I used for the process. I don't hardly ever use exclude patterns, so I'm not going to worry about that one. We can just do a find for anything of interest. So if there's a particular method that we care about, I can do a find for it. And then the start and the end are the time metrics, so like the counter values that we started and stopped at. Okay, so with that, let's see what we have. So we have a bunch of different events, but let's go ahead and look at this a different way. So I'm going to go over to the call tree view, and let's pick something of interest. So let's pick one of these threads here. Actually, that one's doesn't have anything useful in it. Lots of broken stacks. Interesting. It's going to expand. Okay, so looks like today this is having issues. So maybe I did need to merge or have it collect symbols or something for some reason. Normally I don't. Okay, so rather than rerun this, let's go ahead. We'll look at the other trace that we already had. So I'm just going to pull this one up. I won't have to do any filtering for this one. And see what we can learn. Figure out where the window went. Okay. Okay, so event stats. So these show all of the different events that were captured. So this is the provider that we looked at earlier. You can see we have the garbage collection ones, and we have a bunch of different events. We see how many times the different events occurred. So for example, we grabbed 789,000 stack traces. And we can inspect any of these and the time at which they occurred. So let's go ahead. We'll jump into thread time. And now we have a more useful view of the code. So this is more typical to what I would expect to see in the other view that PerfView happened to consider broken for today. So we can see that, yeah, we did spend a lot of time in application insights telemetry. We get the methods, but we can do a bunch of other things. So let's just kind of look through here. Actually, I want to go through, and let's group this by class name. And That way, what we can do is we can come over here. So I just scroll down the list saying, where's my code? Perf controller. And then there's this forced synchronous wait. That's interesting. We didn't see that in that report. So let's go ahead and look for perf controller forced synchronous wait. Let's see if there really is an issue there. Perf controller forced synchronous wait. And sure enough, we have a get awaiter get result. So just using that, we found we already have another method. There's this random delay. Well, we'd have to figure out how to fix this one because I don't know how this caller is used, and that's not the purpose of today. So we're going to kind of ignore that for now. We do have more information on, or more evidence for that console change. So here's console, here's console, here's console. So definitely a lot going on there. You can see that we're doing some compression of the HTTP requests, and interesting. We can see the application insights definitely is running and serialization costs associated with that. Okay, so rather than spend much more time digging into the troubleshooting there, or I should say this particular application, I want to look at some other tools that we have. No, actually, there's a couple of things here that are particularly useful. So if we go to this flame graph, what we get is a graph that shows two things. I'm going to go ahead and draw in blue. So going in this direction, we have time. So that's time. Going up is call stack depth. So let's call stack depth. Where the bottom is the lowest stack, so that's like the start of the process. Okay, so with that, if I were to come down here, you can say, okay, well, that's the root of the process, non-activities, and then most of the threads fall under that category. And I can just walk up the stack until I get to the very top. So this particular thread, and it's whatever thread happened to be selected in this call tree view. So right now it's just this process level. I could expand this and we could narrow this down a little bit more. But whatever thread is selected is what I'm going to see here. So anything that is wide, like from left to right, means it's taking up a lot of time because that's that access. So if I come over here, I said, oh, this one's a locking. We saw that on that report that we generated. So why? Oh, this one's application insights, quick pulse. Oh, so this is just gathering data on a cadence from performance counters. So maybe not horrible. But what about this one up here? File IO. Well, where did file IO? I can just drag my mouse down. AI server telemetry. Okay, well, we have apparently application insights doing a bunch of file IO. That one is a little surprising. I wasn't aware that it was going to do file IO. But see, we're learning good things. It's doing more file IO. Come over here, more file IO. Wow. And we could change to other threads. Okay, so let's see. On channel 9, which was Microsoft's kind of news little station, there were a lot of good videos on how to use PerfView. Channel 9 is kind of defunct. I believe there is a GitHub repository that has a link to all of the videos that are still available. So I don't know what the good videos are because I watched the Channel 9 ones a long time ago. But there should be good training on how to use PerfView to do some of that. Okay, so one of the things that I did want to jump into now, though, so I'm briefly going to talk about another tool, which is this UI for ETW. I have this one running already. And this is a tool that you can run all the time. If you leave it tracing, very little impact to your performance because it just uses that kind of kernel ring buffer. And then I would typically enable CLR tracing for the things that I'm interested in because I'm interested in .NET. At any time I find that there's an issue, I just go hit save trace buffers. So if my machine's working great, then all of a sudden it pauses and I'm like waiting 20 seconds before it does anything. I'll come in here, I'll hit save trace buffers right here. And then that will then give me a capture of that particular moment in time. So I love this tool for just figuring out what's going on with my machine. Okay, so that's all I'm going to say. It generates an ETL file. You read the files in PerfView. You can read the files in other tools, and we're going to take a little bit a look at more of those right now. Okay, so briefly, other tools. We're not going to spend as much time in these, but SpeedScope is SpeedScope app. It's just a little website. When you drag a file or browse to a file, it does not upload it. This is all in browser. So you could do a network trace there. I'm going to go ahead. I'm going to pull up File Explorer here. I'm going to go to my ctemp demo. Actually, it should be demo 1. And we generated this SpeedScope file. So what I'm going to do is I'm just going to drag it in. And then it's going to load it. We got this little progress bar. It does slow down. And here we are. So this is another view of the same information that we have. Right here, we get a view of all of the threads. So we can see how many threads, what the different threads are view, and we can switch between them. So this is the full 2 minutes and 30 seconds. And you can see we sat here and managed threads or an unmanaged code time. Now, if we look at the stack trace right here, Microsoft extensions, hosting abstractions, that makes sense. This is the main program. It's waiting for all my stuff for ASP.NET Core to finish or something to kill it, which is not going to happen. So this is perfectly healthy. Now let's come to one of these .NET Thread Pool ones. Again, so some people call this a flame chart, just like the flame chart that we talked about with PerfView. Other people say, no, this is not a flame chart. This is an icicle chart. It's completely different because it goes down instead of up. That's the only difference. Stack goes down. Okay, so if I scroll down here, now I'm at the top of the stack, and what I'm interested in is anything that I can control. So unmanaged code time. Well, why would something be sitting here? This is a thread sitting here for 21 seconds waiting. Well, I don't know. So let's just kind of scroll up. You know what? It might take a long time. Oh, Microsoft Application Insights, redirect HTTP handler. You know what? This might just be a pain. So what I'm going to do is I'm going to go Control F here, and I'm going to say, you know what I really care about? It's anything that has App Insights test. Now, what you're going to notice is if I come over here, you're like, wait a minute, I don't see Application Insights test. Well, you do see Application Insights, and then it's actually like doing a wildcard between every single character. So if there's application insights and then a T somewhere after that, and then an E somewhere after that, and then an S somewhere after that, it highlights it. But what that means is I have now highlighted anything that has my code and then a few other things. I haven't figured out how to do a search that's not fuzzy or like a regex search. But anyway, so this is none of this is code that I control. This is all application insights. So interesting. Maybe this is a background thread that it started and managed, so maybe that's fine. So that's also application insights. Oh, wait a minute, right here. This is my application. So I have cart controller, try or log required item delay async. So if I scroll down this thread, question is, oh, unmanaged code time. That's bad, right? In other words, that is time where the CPU, and that's 1.14 seconds, that CPU is stuck. It is waiting for something to happen. So let's go back up to what that method was. So this is the last one highlighted. So I have this add item method. So we're going to go back to our code. I'm going to look for that add item method. And let's see, items, add, try log required item, await required item delay. So there's a task, that's async, so that wouldn't show up that way. So what about this add would be slow? I don't see it offhand, so go back. So we've add item. We have async, trying to get a result. And then we could scroll down. Oh, look at that. We still have logging. Oops, I think I switched over. maybe I'm not on the same one. Anyway, unmanaged Serilog console. Oh, that's right. This is the first trace. That makes sense. So here, because we had the logging, because the second trace didn't work, so we don't have the newer trace. What we're seeing is that this time right here, we're waiting for the console so that we can write to the console without having interleave text between threads. Okay. So speed scope, and I can zoom in on a specific area. I don't have to look at the whole thing. So I can kind of move that view around. The left heavy view says, you know what, regardless or ignore how things actually occurred, just move the most heavy or performance worst methods over to the left. Now I can see, oh, it's application insights here. Here's something that's mine, cart item, cart controller add item, which we were just talking about. And Serilog, again, okay, that console logging, it was really killing me. That's not good. But now I have information about why that happens. And I can highlight those methods that are most relevant. Okay, so now we've looked at speed scope. I already talked briefly about this or about the UI for ETW. One of the things that I want to mention is Windows Performance Analyzer. So Windows Performance Analyzer can also load some of those events. So I'm going to go ahead. I just run everything in the command line because it came from Linux. So we'll let Windows Performance Analyzer go ahead and start up here. And then I'm not really going to go into any details, but I at least want to show it. So I'm going to go ahead, File, Open. We're going to go to that ctemp demo 1. And let's grab the ETL file here. Notice that I have the kernel one too. Wow, so most of those are kernel events. If I had disabled that, which I don't care about for this purpose, that would have saved me a good file size. Okay, now Windows Performance Analyzer is really for performance as a whole. It is not for diving into the stack traces. So what you're going to get here is this is the timeline view, and I can expand it. So these are the different events that take place, and I can hover and I can see who's doing what. If I expand, I can double click, I can drill into processes. So these are the process IDs. But again, something happened, so it says unknown. This is part of the, I don't know why it was corrupt this time, but you know, typically we'll see the process name right here, and we can drill into it. And then we'll be able to drill into the providers, and we can get all sorts of details. So know that Windows Performance Analyzer is another good tool. There is another tool called XPerf, which comes with the Windows Performance Toolkit. Actually, I have it up over here, XPerf. Yeah, Windows Performance Toolkit. So with XPerf, you get the ability to do the same kind of captures. And there's a lot of triggers and things. Like you can say, hey, under this condition, grab the stack traces. Or if this performance counter hits this value, then perform this as a collection. So know that that is another option. And then lastly, let's see, do I have, it does look I still have it up. So I did want to show one other thing, and this is kind of in the advanced scenarios, and then we'll conclude with questions and then complete. And that is, because we're getting all of these events, we can do useful things with them. I didn't really talk about that, but let's say, for example, we've noticed that if we're looking at performance counters or event counters in .NET Core, that we're seeing a lot of contention where like there's a lock or something going on. So we can come over here and I can say, hey, when was there a contentious event happening? In other words, two things waiting for a lock before they could perform that operation. I can come in here and I can just choose one. And then in this case, I haven't showed you a dump. So I'm just going to dump that out to file really quickly. This is a log file. And then you can see the information associated with that. In this case, there's not a lot of them. I get the CLR instance ID. I get the thread ID, the process ID. So there is sometimes more information that's not displayed in the UI that you can get by dumping these out. There's a right-click menu for that. In this case, I want to choose go to. Actually, I don't have go to, so I must be open. Let's do, I'll do any stacks. And then what this is going to do, and for some, it doesn't always go right to it. So I'm going to just do a search for contention start. Okay, so now that it's here, I'm going to go to, and I want to go to, I think it's callers. And now I can see who had the contention. So this contention was caused by, and I can expand this, Serolog. So we can see we have a couple of different places where it's writing to the console and there was contention, right? That's super useful. If I expand this one, we could see, oh, it looks like there's going to be a couple of different places where there's contention within application insights. And then there's another one with application insights, and then there's a Kestrel one. That one might be interesting. Okay, that's more about Kestrel than I know, so I'm not going to investigate. I don't see my applications code here. But note that we can actually go from the events to what was happening and what code was called it, and that is super powerful if you know how to use it. Okay, so that was a lot of different things that we covered pretty quickly. But now hopefully you have an idea, some of the power of the tools associated with .NET and its performance tracing capabilities. So with that, we'll open up to questions and go from there.
Could you give us an example of a performance issue that you found with these tools and were able to fix?
Mm-hmm. So I've had to use SpeedScope many different times to find issues where there was code that intended to be async, but accidentally blocked threads. So what I had to do is I had to get a trace. That's a difficult issue to find in PerfView, so I exported it to the SpeedScope. And then I just kind of looked through the threads saying, okay, like right here, for example, here we have this unmanaged code time. So this is one of the things that I've looked for in solving that issue. I said, okay, here, and if I hover over it, 12.66 seconds in unmanaged code time. So I have this method, random delay between milliseconds. And we fixed that one already. So if we had the newer trace, we wouldn't see this issue. But let's go back to the code. So that random delay between milliseconds, right here. So this is the one that we had, the thread.sleep. So by looking at that SpeedScope file, I was like, well, wait a minute. This method, I should actually, in my case, it was, I don't expect any of my code to be slow unless it's on IO. In other words, if I'm going to the database, sure, that can be slow. If I'm writing something to a network socket, sure, that can be slow. But those aren't slow as in CPU. And what unmanaged code time means, I'm going to go ahead and disable that. What unmanaged code time means is that thread is blocked and appears to be using CPU the whole time. And that's bad, right? So anytime I see unmanaged code time and a big chunk of it, I was like, well, how did we get here? Like, why would I be spending 8.81 seconds doing the same operation? That doesn't make sense in my types of applications.
Nice, thanks.
Yep. Other questions? Okay, that was kind of a whirlwind. So apologies if it was too fast to be incredibly useful. But like I said, my goal was really to let people know that these tools exist, that because of the details that go into the problems they attempt to solve. It does require a lot of knowledge. So the goal was not to teach you all of the details about any of them, but rather to let you know that they do exist. They are powerful. And now, as time permits and as you have problems that need them, take the time to